Hey everyone, this is Dr. Walker. This is video 225. It's called Capacitors in Series. We're just going to be looking at capacitors hooked up in a different way than parallel. When capacitors are hooked up in series, it looks like the picture here, where you can see they're connected, and I have written they're connected with no junction in between. But the best way to think about it is that there's just a single path. If you look at the battery and trace out the wire to the left and then upward, and then there's nothing that splits up or anything, there's just a single path. Another way to think about it is that two plates are directly connected, so you can see the right plate of capacitor 1 and the left plate of capacitor 2 are connected with a straight wire. And by straight, I just mean with a single wire without any junction. So that will make your capacitors in series. If they're connected and there's just a single wire connecting them, no junction in between. So if you had another wire like this, for some reason, again, it wouldn't cut through the battery, but now they wouldn't be in series because there's a junction in between. Let's take a look at properties of capacitors in series. The first thing is that the potential differences across each capacitor add up to the battery voltage. In parallel capacitors, the voltages were the same on all the capacitors, but in series, they add up to the voltage from the battery. I like to do the same kind of analysis that we did earlier. So you have your battery here. So what you do is pretend this is 9 volts and the positive terminal, and the negative terminal is 0 volts. And then you look at that conducting wire, that equipotential surface, where all the points are at 9 volts. And then you look at the one on the right, that's at 0 volts. So you can see that the left end is at 9 volts, and then it goes all the way down to 0 volts. There's going to be a potential difference across the first capacitor. We don't know what it is, it's going to depend on the capacitor, but let's say there's a potential difference and it's negative 4 volts that you drop, then that means that this point over here would be at 5 volts, and then you'd have a potential difference of, and let's just use positive numbers to simplify things. Then you would have another potential difference of 5 volts between these plates to get down to 0. So you can see that the 4 volts plus the 5 volts across capacitors 1 and 2 add up to the voltage from the battery, which would in this case be 9 volts. So that's the first property of our capacitors in series, and all of these equations are provided on the equation sheet. The next property is that the same charge is stored on each capacitor. In parallel, the charge is added up to the charge on the equivalent capacitor. So I didn't have a picture of it here for some reason, but we can draw this circuit here with the two capacitors in series, just like we did with the capacitors in parallel. This is our battery down here. So we can simplify these two capacitors to one equivalent capacitor, just like we could simplify the two parallel capacitors. So this is C equivalent here. This is C1 and C2. What we're saying now is that all the capacitors, C1, C2, and the equivalent one, have the same charge. And the best way to think about this is if you think of, we talked about the negative plates building up because of the battery and pushing those negative charges away so that you're left with a positive charge on the other plate. Well, all those negative charges that get pushed away from that first capacitor, they land on the other capacitor, and then that pushes away all the negative charges back to the positive terminal, so you're left with a net positive charge here. So they all have the same charge, and when you simplify that to a one equivalent capacitor, that one will have the same charge as well. And finally, the last property, the equation looks a little bit weird. I call it the 1 over equation. That's just what I call it, 1 over, right? Because it's 1 over C plus 1 over C. So to derive this equation, you could again start from this top equation here and do some manipulation to end up with this equation. I'll leave it to you if you're interested. But what's important about this equation is to understand how it works. What this says is that 1 over the equivalent capacitance equals 1 over C1 plus 1 over C2 plus how many ever more capacitors that you have in series. So the equivalent capacitance is actually going to be, think about it, is it going to be greater or less than any of the individual capacitors? It's going to be less. And I want to show you this to you with a quick example that's going to be very useful in a lot of problems. Let's assume that C1 is equal to C2. Let's say they both equal 10 farads. We usually work in microfarads, but just to simplify things. So if you're trying to find 1 over C equivalent, just plug those numbers in. 1 over C equivalent equals 1 over 10 plus 1 over 10. So 1 over 10 plus 1 over 10 is 2 over 10. That's not what C equivalent is, right? That's 1 over C equivalent. So to find C equivalent when you're using this 1 over equation, then you have to take the reciprocal of the answer to get the C equivalent on top. So 10 over 2, which is 5. So you can see that the individual capacitors had a capacitance of 10 farads, but the equivalent has a capacitance of 5 farads, so it's going to be less. And another reason for me showing this example is this is kind of a shortcut. Whenever the capacitances are the same of the capacitors that you're simplifying in series, if you have 2 capacitors, then the equivalent capacitance will be half, and you don't even have to go through all the steps. If you have 3 capacitors, then the equivalent capacitance will be, what do you think? If you know, put it in the comments and we'll sort it out there. So let's move on to one question. Which of the following capacitors are connected in series? We've got the same circuit as before. We've got C1, C2, C3. So pause the video, think about it. So we already said that 2 and 3 were connected in parallel, so they cannot also be connected in series. That would not be possible. If we look at C1, you may think, oh, maybe C1 and C2 are connected in series. But they're not. They're not directly connected. There's a wire here between C1 and C2, but there's a junction. We said for C1 and C2 to be connected in series, it would have to look like this. It would just have to be a single wire connecting them with no junction in between. Since there is a junction right here and there's another wire, they're not in series. So the answer is actually that no capacitors are connected in series. So we're going to be working with capacitors in series and in parallel. In the next video, we'll have combinations of series and parallel put together. So you will need to analyze them and be able to identify these combinations. I hope that you'll have a fun time with it. It's one of the things that I enjoy doing. So I will see you in the following video.